Welcome to another episode of our podcast. This is Adhika Maurya, co-founder of STEMExpedition, an organization that takes you on a fascinating journey of mind-blowing STEM inventions. As always, we are here to explore some high-level science shit. Our host for today's episode is Kavya Bhanushali, who is a budding quantum researcher. And I must say, she's the kind of girl who was solving integrals while the rest of her class was busy learning a plus b whole square. Over to you, Kavya.
Thank you, Adhika. Now, before we get into today's episode, let's take a moment to welcome Professor Sandeep Goyal as the host for today. Professor Goyal, welcome. Dr. Goyal is an assistant professor at IISER Mohali. His work in quantum tunneling and photonic quantum computing is fascinating and rather mind-boggling, I must say. It's almost as if he's the dummy of photons, waving his quantum wand and making particles dance the cha-cha in ways we can't even pronounce. Good morning, Professor Goyal.
Good morning, Kavya. Thank you for the invitation, and I'm really looking forward to today's podcast. Just small correction. I'm associate professor at IISER Mohali and a lead scientist at the conference, Indian startup for photonic quantum computation. Over to you.
Okay, thank you so much. Now let's begin with our questions and, of course, with the basics. What exactly is quantum computing, and specifically photonic quantum computing?
Yeah, so this is a loaded question. So in the following sense, first let us start with very simple thing. Quantum computing is a new type of computing which exploits the power of quantum mechanics. Right. So there's quantum mechanics, and we use that to do computation which we want to do with our desktop or laptops or any other computer. We have supercomputers and all. Just that when we exploit quantum mechanics, we can sometimes make it insanely fast. So let me start from quantum mechanics. Quantum mechanics is like a magical world, okay, where strange thing happens. There are strange rules which may violate our understanding and our common sense in some sense. Okay. For example, very simple example, if you have a quantum particle living in quantum world, it can exist everywhere in principle, all at once. Okay, at a given time, it can be anywhere, it can be everywhere. Okay, for example, you might have heard about Schrodinger's cat. That cat is a quantum cat, not really a physical cat, but a quantum cat, which can be alive and dead at the same time. Okay, quantum particles have other properties that they can pass through walls. This is like really science fiction kind of things. Okay, and all this bizarre behavior you can attribute to one thing. That is called the superposition principle in quantum mechanics. Okay, so what it says is, if let us say you have an electron, we all know about electrons. We all know that electrons have spins. Okay, and this spin can be up or down, right? So quantum mechanics allows you to have the electron in both up and down spin at the same time. So electron can have spin up as well as down at the same time. This is what superposition principle says. Okay, so these are some of the properties of quantum mechanics, and I have just listed one. There are a couple of other things which are very fascinating and very counterintuitive. But how do we use it in computing? So now let us talk about computing. When we have traditional computer, which we generally call classical computer, as opposed to quantum computers. So we have this traditional computers. They use bits. A bit is something which can take values 0 and 1. Okay, so it need not be numerical 0 and numerical 1. It can be on off, it can be up down, it can be any two states. Okay, in our electronic circuits we have uh, uh, switch on and switch off. That kind of are the states, 0 and 1 states we have. Now if you have 10 bits, then all of them can take value 0 or 1. So in total there are 2 to the power 10, which is about 1000 configurations. In the sense, there is a sequence of zeros and ones. Okay, how many such independent sequences we can have? That's 2 to the power 10, which is 1024. That is approximated to 1000. If we have 100 bits, then how many sequences we can have? They will be 2 to the power 100. That will be 10 to the power 30. It means 1 followed by 30 zeros. roughly of that order. So there will be that many configurations. Now, if we want to do some processing on using our classical computer, then it will start with one such sequence. It will navigate through those sequences and find the sequence which resembles our answer. In quantum mechanics, we use quantum particle to make bits, and they are called quantum bits, so qubits. They can also have 0 and 1 state. So again, 0 need not be numerical 0. It can be spin up of electron. It can be magnetic flux quanta. So it can be any other property like the polarization of photon. So it should have two values. We call it 0 and 1. If we have 10, but quantum mechanics says that it can exist in 0 and 1 simultaneously, right? So if we have 10 qubits, then there are like classical bits, we have 1000 configurations. If we have 100 qubits, we have 2 to the power 100, that is 10 to the power 30 configurations. But quantum mechanics allows our system to be in all the configurations at the same time. So when we want to do the processing, it can do the processing on all the configurations at the same time. Okay, in that way, we can achieve huge, humongous parallelization in computing, which can reduce our time of computation, our limits of computation, our space required to do computation to insane number. Of course, there are very limited applications we could find till now, but we don't have a physical working practical quantum computer. Once we have that, the number of applications will also increase. So that is the part about quantum computing. So how we do quantum computing in a basic sense, this is the basic principle behind quantum computing. How do we do photonic quantum computing is just that we have to make qubits, quantum bits with photons. We can use single photon. A photon is the minimum amount of light you can have of a given frequency. Let us say we have red laser, and we start reducing the light of that laser. Okay, by putting filter, we start reducing the intensity of that laser. Is it possible to have like infinitesimal energy, light, means very, very small amount of light? What is the minimum light we can have? That minimum light is called photon, and it's discrete. You cannot have, it will be either 0 or 1 photon. It cannot be half photon or 0.1 photon. Okay, the energy of 1 photon is very small, but still it's a discrete quanta of light, which is a photon. Now, if some laser has a polarization, all the photons in that will have the same polarization. So if we have 1 photon, it will also have polarization. And we have 2 independent polarization states. We can say horizontally polarized photon or vertically polarized photon. We can use these 2 polarizations as our 0 and 1s of our qubit. So 1 photon can behave like a qubit. This is one way of doing quantum computation. We use this now for the computing. And then we can use beam splitter, we can use wave plates, we can use other things to implement all the transformations to arrive at the right answer. This is not the only way of using photons to do quantum computing. We can send 1 photon through 2 paths. Okay, let us say we have 2 waveguides or 2 fibers. Okay, so photon going in first fiber or photon going in second fiber can also behave like 2 independent states of light. So we can say it's 0 if it goes in the first fiber, and it's 1 if it can go in the second fiber. It can go simultaneously in both the fiber, but it cannot do half in the first fiber and half in the second fiber. Okay, so that also can be used as a qubit in our system. They are more complicated and involved way of performing, making a qubit out of photons, which we cannot discuss in this podcast, or we should keep it for the later on for more detailed, more rigorous podcasts. But this should give you an idea how photons are used for quantum computing.
Absolutely. So leading on to this, as you already told us, that quantum computing computing presents a lot of opportunities relative to our classical computers. Could you elaborate a little on some of these opportunities which are presented by quantum computers, which can help the real world to advance in certain ways?
So, one example I can think of is which is actually the founding problem or founding algorithm which started the race of quantum computer. That should be the Shor's algorithm. Okay, what it does is, let us say I give you two numbers, 3 and 5, and you want to multiply them, and you multiply and get number 15. But so it's an easy problem. But if I give you number 15 and I ask you to find the factors of this number such that the product of those factors is number 15, then you will have to start from 1. 1 is trivial. Then you will start with 2, whether you can divide 15 with 2. Then you will go to 3, then 4, then 5, and so on. And you will list all the factors of 15. 15 is a small number, so this problem looks very ridiculous. So we can increase the problem. Let us say I have 1,732,000. Okay, some random number. I don't know what how it look on paper, but some random number we take, large number, and I ask you to find the factors of this number. This will take you some time on pen and paper, but on computer it might take a fraction of a second on our classical computers. Now, if I increase, so this 1 million and so on and so forth, I said that is total 7-digit number. Okay, it takes 7 digits to write that number. But if I increase the digits to 20, then our desktops will take few seconds to find the factors. Once we have factor, then multiplying them and getting the answer back is very trivial. So it will be done in no time with computers. So it's a non-reversible problem in that sense. In one way, it's very easy to verify, but finding the answer is very difficult. Once we have the answer, it's easy to verify. So if we have 100-digit or 200-digit number, then it will take supercomputers to find the factors of that. Okay, our desktops will never be able to do in the entire age, unless the answers are trivial. Okay, there can be trivial numbers, but there are some numbers, it will be very difficult to find the factors of those. Okay, so why we need to find factors? It seems like a made-up problem. All of our security system, the cyber security, the encryption, and the decoding and encoding, all of that is done using a protocol called RSA protocol. Okay, and that protocol heavily depends on this non-reversible property of prime factorization. Okay, so if I give you, if I have very large number and I can use it as a public key, and one of the factor or the factors of that I can use as the personal private key, and with that I can encode a message and decode the message without anyone listening into it, right? So the RSA technique, prime factorization, become very important. Okay, so but of course that is for the hacking, but Shor gave a method that you can factorize any number. Does not matter what is the size of this number. Okay, whatever number you have, you can factorize it in basically in no time. Okay, but you cannot do it on the regular classical computers. You need quantum computers for it. Okay, so he did not use probably the word quantum computer. He said you need to use quantum principle to factorize a large number. Okay, he gave an algorithm. He said what needs to be done, and then people tried to make that, because once you have that computer, you will be able to break all the encryptions in no time. Okay, so that is one example which I can give you, which is impossible to do with classical computers, but very trivial with quantum computers.
Okay, so as you mentioned, if we are able to simulate Shor's algorithm on a quantum computer, we can break RS encryption. And if that is done, then practically anyone with a quantum computer can have access to any data from all across the world. That is a big threat. So what would be, in your opinion, other than this, the biggest threat which a quantum computer may pose to our human race?
Right. This is this is I always find this kind of question strange, and it's partly my fault in this podcast today, because I mentioned that you can break RSA encryption, but let me first tell them quantum computation and communication breaks the security, of course, RSA security or traditional security, but it provides additional. There is another way of getting security in our messages or in our encryption, which is much, much stronger than RSA. So that is called quantum key distribution protocol. There are many protocols which will provide you absolute security. RSA security, for example, depends on the unproven fact that prime factorization is difficult. And with quantum mechanics, we can factorize it very trivially. So it's not difficult with quantum principles. But QKD secured communication is unbreakable. It depends on quantum mechanical principle. So unless quantum mechanics fails, this encryption is absolutely secure. And about the threats, so in my opinion, any new technology, any new method, or any new device, okay, new in the sense like really fundamentally new device, always brings some kind of anxiety. Okay, so when people build ships to travel on oceans, and so they were used for wrong purposes also, to conquer lands, to attack people. When now, for example, we have machine learning and artificial intelligence, although it has not done much damage till now or any damage till now, people are skeptical about this technology also. Okay, so in my opinion, any technology you have can be used for bad things if it is in wrong hands. Okay, so the right question here should be, what are the potentials of quantum computing instead of threats? So quantum computing, the potential here is really insane. Okay, you can do, it's not just factorization. Factorization was the first problem which was proposed using quantum computers, but search algorithm can be made insanely fast with quantum computing. People have been using quantum computing, or like that, they are developing algorithm for quantum computers to simulate molecular behaviors. So you can, like right now, people do it with the traditional computers, but it takes a lot of time, and it cannot handle very complicated molecule. But with quantum computers, you can handle very complicated molecule. You can change their properties in the computer and get the answer without performing it in the lab. Okay, so this is like science fiction. You might be seeing in many science fiction where they have a 3D hologram where they change couple of atoms in a molecule and the molecules start working. So that can be a reality with the quantum computer. Maybe not the hologram thing, but the whole processing. And what are the impacts of that? You can have faster drug development. You can have very accurate drug delivery system, and the potency of drugs will be very high. So we will be eradicating disease, all the kind of disease, when we have the working, controllable, practical quantum computer. Then people have been using quantum computing in space exploration. Yesterday only I was reading that that was actually about artificial intelligence, but quantum computing is making computation fast, searching fast, so it will immediately affect the machine learning and artificial intelligence front also. Okay, so many of the tasks can be done which are required for machine learning and artificial intelligence can be done very, very effectively with quantum computers. So you see, if we have quantum computer, the progress of science and technology will be exponentially faster. It will be at a scale we can't even imagine at the moment. It's like asking someone in 1940s what will be the impact of computers on society. If I may, in 1943, there was the chairman of IBM, and his name was Watson. Thomas Watson. He made a statement that I don't think there will be a market of more than 5 computers. I might be paraphrasing his statement, but this is what he said, that I don't think there will be a world market of more than 5 computers. And this statement coming from someone as big as chairman of IBM actually slow down the process of computers. Okay, but now we see in my room here, in my study room here, I have more than 5 computers, two laptops and one iPad and 2 phones. So phone is more powerful computer than what they had in 1970s when they were building Concords, right? So right now we can't even imagine what quantum computers can do. But what we can see already, their potential in drug development, their potential in chemistry, their potential in coming up with new material that can like really push the boundary of technology to any level. Okay, so
Certainly. Absolutely. Thank you so much, Professor. That was insanely fascinating to hear about. Now that we're aware of most of the basics, let's take a stepping step forward and let's increase the difficulty of the questions a bit more. Now, do you think photonic quantum computing is relatively better than other types of quantum computing, such as maybe superconducting qubits or maybe trapped ions?
uh, so I think like you're asking me this question because I work in photonic quantum computing, right?
Yeah.
So the idea is till now we do not know which platform is better and which is not. Okay, if you see IBM and Google and Microsoft, they are working on superconducting quantum computers, right? And IBM has made more than 400 qubits. Okay, although it's still not practical, we need thousands, if not millions, of qubits to do anything practical. Okay, but they have reached 400. In trapped ions, there are a couple of companies. I think they have reached about 20. But in photonics, we don't have a single qubit. I shouldn't say single, but we don't have any boostable number of qubits. Okay, so if you look at the current status, photonic quantum computing does not stand anywhere on the map. But now you see what are the difficulty. If you have quantum computing, superconducting quantum computers, then superconducting qubits needs to be kept on millikelvin temperature. Let me emphasize what is a millikelvin. So our 0 degree Celsius, where the water freezes, that is 273.15 approximately 273.15 Kelvin. Okay, so 273 degree below zero will be 0.15 Kelvin. Okay, we have to go 10 times smaller than that. Like instead of 0.15, we need to have 0.01 Kelvin or 0.001 Kelvin temperature. We need that small temperature to make the superconducting circuit behave properly quantum mechanically. So any system like superconducting circuit here, you can make it quantum mechanical for some time, but because of temperature and all, even this small temperature, it loses its quantum nature and it starts behaving classically. Okay, so that time in which it becomes useless, that is called the coherence time of a qubit. Okay, and if you have one system, maybe you will have a microsecond of time. Okay, so it's random, right? It's average, it's microsecond. So some system might last for a millisecond, some system might last for a nanosecond. Okay, a microsecond is 1 millionth of a second, right? So and a nanosecond is 1 billionth of a second. So if you have two superconducting circuits, 2 qubits from superconducting circuit, then any one of them failing will destroy your computer. So your effective coherence time becomes smaller. If you have 100 qubits, it will be much, much smaller. Why coherence time matters? Because all the processing you have to do has to be in this coherence time. After that, it's useless. Okay, so if your system can work only for a microsecond, so you have to perform 1,000 operations in that. So your operation time should be it should be a nanosecond, right? So that's how, now you see, if we have 400 qubit and we want to go from 400 to 1000 qubits, first our coolest time will come down. More qubits means more number of operations we have to do. So it means between the operations, time is reducing. It might be picosecond, it might be femtosecond. Okay, so in that way, going increasing the scale with superconducting qubit is difficult. Okay, same with trapped ions. To trap an ion, we need almost perfect vacuum and full control. And then you have to trap many ions. And this is the difficulty level that from 20 to 200, if you want to go, the technological development you have to do is like really Nobel Prize worthy. And you have to do so much of technological development. And again, low temperature and all those things are still there. Temperature is always a killing factor. In photonic quantum computing, we believe that temperature factor is minimal. Okay, just to produce very good photons and just to detect very good photons, we need low temperature instruments, but all the processing can be done on room temperature, on ambient temperature. So in that way, even though till now the progress is not much in photonic quantum computing, I believe that once we cross the first hurdle, scaling will be much easier. So every technology is coming with its own pros and cons and all the factors. Okay, does that answer your question?
Yes, it does. Okay. So now, if we were to make quantum computers available to the masses, we would need to find more economic and more practical ways to generate photonic qubits and produce better equipment for detecting the photons, measuring their states, and of course, noise control. So, so according to you, what are some current cutting-edge ways to increase the efficiency of quantum computers, especially in reducing the noise and doing more noise control?
So I can give you details about photonic side. And of course, your question is on photonic side. So now people like traditionally how people were creating single photon. We should understand that first, right? It's not that we just have a laser where we reduce the intensity and it start giving us single photon. It does not work like that. Okay, so what people do is there are some here. Okay, they are called non-linear crystals or non-linear material. So in that, if you put some light, okay, let us say you are putting a light of wavelength 1064 nanometer, okay, which is infrared light. So it can double its frequency, so half its wavelength. So what happens is in these nonlinear crystals, they can take some light and can convert it into in some other light with some probability. It means not the whole intensity will be converted, but a fraction of that intensity will be converted into same energy but lower wavelength light. Okay, so I gave you example of 1064. So that can be converted into 532 nanometer wavelength light, which is green light. So we have crystals. We are working also on with those in our startup here. So we pump the crystal. We send the light of 1064 nanometer, which is infrared, and output light after some adjustment, after some alignment, the output light is green light. Conversion rate is like, let us say 10% or something. And you have seen that. Every one of you have seen that. When you see a green laser pointer, okay, if you open that, you will see that the laser itself, when it is emitting light, the laser inside it, there's small laser diode. That laser diode is actually 810 or 1064 nanometer wavelength. So it's not visible. It's infrared. And then there will be a couple of crystals and couple of lenses. They are converting this 1064 into 532, which you see coming out. Okay, that also is a warning sign here because the filter they are using is not 100% accurate. So with that green light, you have infrared light also coming out in the laser form, And if there is a prism kind of thing or some glass kind of thing, it might happen that the green light and the infrared light get separated. You won't even know, but your eyes will be burning. Okay, because infrared light you can't see and it's very, very dangerous. Okay, so I will suggest not to use green laser pointer in your presentations and all. But that being said, that process, okay, is something which converts light from some wavelength to its half of the wavelength. Half, I'm just giving one example. There are other ways of converting into different wavelengths also. So what is happening here is actually when you do this experiment properly, so your one photon, okay, is getting converted, or two photons are combining to make one photon. Okay, two photon of 1064 are getting combined to make one photon of 532. Okay, so you can reverse the process also. You can send 532 and you can create 1064. Okay, so what happened? You send one photon of 532, like we are sending a lot of light, but let us assume what is happening at quantum level inside it. One photon of 532 is getting converted into two photon of 1064. Okay, but most of the 532 is passing through. Okay, it's not getting converted. A few of those photons are getting converted into 1064 pair of photons, and that pair is like really correlated, and they're going in different direction. If we align the system in a proper way, 532 will just pass through straight, but 1064 will come out in a cone. Okay, like on a circle. So what happened after that is like we put detectors in front of those photons in the path of the photon. If we detect photon of 1064 in one arm, in one place, we know that on the opposite side, there will be another photon of 1064. Okay. In that way, we are sure there is a single photon of 1064 coming in the other arm. So we use SPDC, it's called spontaneous parametric down conversion, the whole process, SPDC. So we use this process to convert one photon into two photon, or lot of photons into pairs of photons. And then we perform measurement on out of those pair, we perform measurement on one, and we know there's a single photon on the other side. This is the way of creating single photon traditional. But in this way, you want to be sure that you are getting photon at a particular time, right? So you send pulses of 532, let us say, and in pulses you will get photon pairs out. But that probability of converting a single photon into a pair of photon is very small. It's 1 in a million to 1 in 100 million. It's that small. If you have 100 million pulses, only one pulse will have a photon pair. Okay, so in that way, it's very probabilistic. It's useful for certain tasks, but maybe not for quantum computing, where we need a lot of photons, single photons at a very predetermined time. So for that, people started doing like they have an atom inside a photonic cavity. So what happened is single photon or light interacts with single atom very weakly. It's basically no interaction between a single photon and a single atom. But we can have two mirrors parallel to each other, and then we put light in. So the light will be bouncing between the mirrors. And if we put an atom in between those mirrors at a proper place, then we can make the same light interact with the atom multiple times. In that way, we are increasing the interaction between light and atom by these two mirrors. And this mirror configuration, there are many other also, but this the simple example I gave you, this mirror configuration is basically called optical cavity or photonic cavity. Okay, so with photonic cavity, we can increase the interaction of an atom with light. Now, if you have atom of like you have certain atom and the wavelength you are interested in for the single photon, it has those energy levels. So there is a transition in the atom which will produce that single photon with a proper wavelength of light, right? So now what we can do is we have these two mirrors, and we can put an atom in between, and we can pump light from the top. Okay, we can send very intense light, intense laser from the top, so that the atom get excited. Okay, and there's a then when it gets excited, it's single atom, so it will emit single photon. So when it emits, it can emit everywhere, but with this cavity, we can force it to emit in the direction of cavity. And there is a proper way of doing it. So in that way, you can produce single photon with reasonably high accuracy in time, arrival time. That is one another way, which is people are exploring now. So this atom need not be an atom. It can be anything which has two energy levels of appropriate difference, energy difference. So people are exploring quantum dots in this way. People are exploring the defect centers in diamonds. People are exploring many other systems to produce single photons. And the success rate and fidelity of producing single photon is very high with this. Okay, this is the progress in the single photon direction. We have to not just produce single photon, we have to measure them also. And in measuring single photon, we need to measure really a single photon, not just light. So it should be able to, whatever detector we have, it should be able to differentiate between no light, single photon, and multiple photons. Like if we have two photons coming at the same time, it should be able to tell, no, we are getting two photons, not just one photon. Okay, so that kind of discrimination is important when we talk about photon detectors for quantum computing. So one very basic way of doing it, okay, which not it does not differentiate between 1, 2, and 3 photons or many photons, but it can still tell you whether there was a photon or not. Okay, so for that, what we do, there is something called diode. Okay, so diode is a kind of miracle gadget, let us say, or electrical component which revolutionized the digital world and which or electronics and everything. Okay, what it does is it's like a resistor. If you bias it, if you send current from one direction in the diode, then it will allow the current to pass, but from the other side it will not allow the current to pass. Okay, so that's the basic characteristic of a diode. But in the reverse direction, if you force really hard, okay, then at some point it will break down the diode and lot of current will suddenly start passing through it. Okay, and how do we make current pass through something? We just apply voltage. So forward bias is voltage is when we pass the current in the allowed direction, and reverse biased is when we allow when we try to pass the current in the forbidden direction. Right. So we can have a diode and we can reverse bias it to the level that little bit more current if we put in, it will break down. Okay, so we just almost saturate it just before the breaking point and stop there. Okay, now if you shine light on it, it will cause the imbalance and it will cause the breakdown. Of course, it's easier said than done, but people with the technology at hand have realized such systems with these diodes that they critically bias reverse bias it. Okay, and as soon as some light comes on top of it, it will just break down. It will show a lot of current. Then you know there is a there are photons in it, but it's still not single photon. It can be one photon, two photon, many photons. But this can be used very efficiently in the processes where we want to know whether there was a photon or not. Okay, whether the photon has arrived or not. So, but to discriminate between 1, 2, and 3 photon or many photons, people have been using something called superconducting nanowire based single photon detectors. Okay, so what they do, they have superconductors. They make very small nanowires, nanometer thick wires of those. Then put a mesh of those wires. Okay, and of course we have to keep them at cryogenic temperature, which is close to 1 Kelvin. And when the photon comes and hit these wires, then locally at on those wires, uh, they lose their superconducting nature. They become normal conductor, and that normal conductor can be verified immediately outside the circuit. So we know one photon has come. When two photons come, then this might have more resistance than single photon. Then you can say there were two photons, and so on and so forth. There are ways of detecting it, but the efficiency we can detect it with is not more than 93% for single photon. If you have two photon, then it's close to 75 or 80. If it is three photon, then it's close to 55, and so on. So in this direction, people have been trying with different material, different techniques to increase the efficiency of detecting single photons. But this is the best we have, the superconducting nanowire-based single photon detectors.
Dr. Sandeep, how about we let our fellow team members ask the questions they encountered during this whole conversation?
Sure.
Yeah.
I really appreciate the opportunity to learn from your wealth of knowledge in quantum computing, like your passion for your subject. It's really amazing. So let's
Thank you.
get further with the question. So my question is, what are some of the major challenges or obstacles that researchers are currently facing in developing practical photonic quantum computers?
So first is the biggest. You're saying in India or worldwide? The question is worldwide, like in the science community, or in India, what the problems we are facing?
About like both.
Okay, so the very general answer is the confidence. Okay, that people took some time to realize that we can actually make a quantum computer with photons. The theory is there, but to get a confidence that you can really do it with photons also, it took some time. First serious effort was in 2016, around that time. It's a company named Xanadu in Canada. So they started this whole approach. I don't know if other people have also done it before that, but that is what I know, and a couple of my friends were working there earlier. They started, and after that, you can see a few more companies coming up with photonic approach. Okay, but still no viable decent number of qubits they have demonstrated. They have not demonstrated anything till now. Okay, something which can be used, or but with these attempts, some more people have become confident. Okay, in India, I think a couple of research groups are attempting following quantum computer, but serious effort is by our company, Confluence in Bangalore. So we have put quite a bit of resource and effort, and we have some roadmap that we have to show something by 2025, and it seems very feasible at the moment. Okay, so that is the one thing, that unless you have the attitude toward making something, it will not be done, right? But now people are getting some confidence, so I am hopeful soon, or soon more people will attempt, and then the chances of getting a viable photonic quantum computer will be a reality. And technology wise, so there are multiple ways of creating a photonic quantum computer. Okay, so everything has its own benefits and drawbacks. People working with single photons, they have the problem that creating single photon is very difficult, detecting single photon is very difficult. People working with continuous variable quantum computing, okay, in which you don't take single photon but a bunch of photons in a proper particular quantum state, that people have been trying. In that case, you don't need single photon detector and single photon sources, but creating those complicated quantum states are very difficult. Okay, so people have been trying those things. Xanadu has some approach, and they have demonstrated, I heard something, but not something which can be used for quantum computing. Okay, so basically, at the moment, fundamentally, I don't think there is any obstacle. It's technology only, and over time, technology is getting better and better. And soon we should start seeing some outcomes from all these initiatives.
So thank you, Professor, for such an insightful session. So my question is, approximately how much time do you think that it will take us to achieve a fully functional quantum computer?
Oh, that is, I would not want to give any number on this thing, okay? But the thing is, if you want to practice, okay, like working on quantum computers and all, then there are some quantum computers available on cloud. Okay, like IBM has a couple of the quantum computers which you can access sitting in your home. Okay, so even if IBM or Google or Xanadu or Confluence come up with 1,000 qubit computer, it will not be a general purpose, viable, practical quantum computer, and surely it will not be in your home. It will be just one copy sitting in some lab, and you can access it from your laptop, right? Sitting anywhere in the world. So it will be that kind of thing. Okay, just look at the progress of classical computer over time. In the beginning, IBM made these machines, right, which was used by NASA and many other, and they could do like they were boasting that they can do 35,000 calculations per second. 35,000. Your cell phone can do more calculations now. Okay, and their computers were using the power of the entire city. At that time when they used to turn on the computer, the lights used to go dim in the entire city. Okay, and from there in 60-70 years we have reached to the level that we have basically on a fingertip you can have a computer now. Okay, there are such small computers. So soon you will be able to access the computers. If you have a very specific problem to solve, for example, the some of the car companies, okay, they want, because they have now autopilot and they want to track all the traffic and all those things, so they want an optimization algorithm so that their cars can navigate very efficiently. Okay, for that they have taken the help of quantum computers. So companies designed very specific computers which will do this optimization for them. So in that way, people have been using some version of quantum computer for some practical purposes. But it's a problem-specific task. General purpose require uh, much more difficulty, many more number of qubits, much more control. Okay, that will take some time. You will soon, like by the time you finish your graduation and all, you will be able to use some quantum computers. Okay, but something which you are familiar with, this classical computer, I think that will take some time and some patience also from the users. So I don't want to put any number on it, because the history is the witness that whenever someone has put any such number, they have been wrong, like really astronomically. That statement I told you from the chairman of IBM, right? How wrong he was.
Good afternoon, sir. Before asking my question, I'd like to tell you something that no one actually put any light on. You talked about QKD and we talked about photonic computing. And now this was a topic that was actually much debated in our group that we wanted to work on this, like developing a QKD model, maybe a theoretical model. That was a topic that came up, and just going through this session, it was very insightful because now we actually know what are the things we need to cover. Anyways, moving on to the question. We know that quantum computers are extremely sensitive to the computations. We need to maintain like what near absolute zero temperatures and such. And moving in a similar pattern, even small noises affect our computations, our calculations in quantum computations. So, are there any possible viable solutions that can actually help us reduce those requirements, that there should be no noise or anything of that sort?
Yes. So the same problem happens in the traditional computers also, classical computers also. You have bits, they are something which can be on or off. Okay. Now, how do we get rid of those problems in our classical computers? There's a field of there's a field, entire field in computer science. It's called error correction. Okay, so they work on this, like how to remove the error, how to mitigate the error, how to control the error, or how much error is allowed in your system. Okay, so these errors, this better and better algorithms for error corrections and better techniques are what is giving you this high HD videos and very clear sound quality and everything you do nowadays on internet. Error correction is what is responsible behind that. The same, not the same type, but the same branch, error correction, exists in quantum computing also. They talk about, like, if you have a particular way of creating a quantum computer and working on it, then what kind of errors are allowed, how the error will propagate in your system when you increase the number of qubits and number of operations, how this error will propagate, this will increase, and what are the kind of operations you need to perform to remove those errors. So whenever we are working with quantum computers, we have those error correction models in our mind before we design the kind of thing we want to do on these quantum computers. There are two kinds of error corrections. One at the level of physical qubits. So your photon, when we are using the polarization, maybe in your system there is something which is changing the polarization of your photon, right? That will give you an error, right? Maybe while photon moving in a fiber, it gets lost. We lose the photon. That will give you a physical error. Okay, so we work on that, how to remove that error, that kind of error. Then these are photons, right? Now they will become qubits. Okay, maybe not one photon, I take 2 photon or 5 photon as 1 qubit. Okay, I'll take 5 photon, and when out of 3 or more number of photons are in horizontal state, then I'll call it 0. And if 3 or more photons are in the vertical states, vertical polarization, I'll call it 1. We can do this kind of thing also. Then it becomes logical qubit. After this, we only work with zeros and ones of quantum computer. Now, in that also you can have error, and those errors are rectified at the logical level. Okay, there are very complicated ways of doing it. That's why, for example, you, like, there is a error correction model for logical error, where to have one stable logical qubit, you need to have 18 physical qubits. Now you see, let us put the 18 number to be a round figure as 20. So if IBM has 200 qubits to show today, no, not 200, 400, they have 413 qubits. So IBM has 400 qubits to show today. Okay, so logically they have only 20 qubits effectively. Okay, because if you want very stable qubit, we are okay with increasing noise and being useless, then we can use all 400. But if we want really perfect error-free computation, then we can only use them as effectively 20 qubits. Okay, and in that way, if you want a practical computer, like Isha asked earlier, okay, when will this computer be available? When we have a million qubits, then they behave like few hundred qubits logically, and then maybe we can do something remarkable with that computer. Okay, so this is how we correct the errors in quantum computer. And of course, like, technically we can't discuss all the things here, but there are ways of doing it with the error correction, and it can also tell us whether the system you have, the protocol you have, whether that will work or not. If the error is more than critical value, then we just discard that.
Okay, so It's been a really one hell of an insightful session, Dr. Sandeep. Right? And for our listeners, I post one last question. What do you think are the best or like certifications and courses or internships that you would recommend to a student who is aspiring to be a quantum researcher? Yeah, from
So,
high school passion to acquiring the PhDs.
right. One suggestion I would give, actually, there are two or three, but let us call them one. So, if you want to get motivated for quantum computing or any field in science, okay, don't read popular books, popular science articles, okay, because the popular science books, popular science articles, they mislead you, and they give you a false uh, feeling for the field. Okay, people, I have seen so many people coming at IISER Mohali thinking that science is so fun and they can do very amazing things like going to Hogwarts and doing magic. But it's not that. You have to sit, you have to do a lot of calculations, you need to learn how to fail. Okay. Because when we do experiment in our lab in Bangalore, in our conference, it took us more than 6 months to just align one laser. Okay, we were failing every day and we were trying again every day. So don't get motivated from popular science books. If you really want to get motivated, if you don't want to read hardcore science but you want to get motivated, science fiction is a better place to read. Okay, but now coming back to quantum computing, for high school kids, students, I will suggest that they start reading about optics. Okay, there is very little difference between quantum mechanics and optics. So all the group theoretical structure, all the mathematics of optics is very much close to the quantum mechanics. In fact, optics is slightly difficult, more difficult than quantum mechanics. Okay, so if your concepts in optics is very clear, then you will understand quantum mechanics very quickly. On top of that, you should study and make your basis strong in the waveband oscillations. Okay, because quantum mechanics, one version of the quantum mechanics is wave optics or wave mechanics. So those concepts will help you immediately in this field. If you want to pursue physics, quantum, the PhD after school, or if you are looking for a path toward PhD, then I will say that IISERs have very good platform. So you can apply for BSMS program to any of the IISERs in the country. All of them support very good quantum groups. So that you can do immediately after your 12th. So there are exams and there are multiple ways of entering IISERs. So you can always try that. Then there are this BTech and BTech with MS kind of courses in India. There you can uh, those you can apply there in most of the engineering institute, but IITs have better groups. So you can apply to any of the IITs and get a BTech and MS kind of degree from there. And after that, you can do PhD. There are a number of good institutes, ISC, TIFR, ICERs, all the ICERs. They have very good PhD programs. So you can always apply to those all those programs, and this is how you can pursue PhD. There are some programs in which in summers, you can go and work in these research institutes. I may not remember often what are those programs, but there are a few you can apply to and go to meet scientists working in these areas. There are many startups coming. If you're enthusiastic enough, they might invite you to do an intern with them for a few months. So with this, I think this will be a good start to work in quantum computing.
So, what about undergraduate programs? What, according to you, is the best undergraduate degree to hold and to get a better understanding for quantum mechanics?
In my experience, I don't think any degree is bad or good. Okay. So like really, like if you are passionate about if you're passionate about learning quantum or anything for that matter, you will do the best in your local college, community college also. Okay. If you are saying that what universities or what institutes give you better reach, better context, then I will say any place from Delhi or Mumbai or Bangalore or Chennai or Hyderabad, where you have larger traffic of scientists coming. Okay, any of those cities will be a better place. Just to make contacts, just to meet people. It's difficult to travel from a small town to a big city all the time. Someone comes, but if the big scientists are coming to your own university and institute, then it's easier to meet them. But the quality of education wise, I think what counts more is your passion than the people teaching you. Okay, so I refrain myself from like making a comment that which one is the better uh, undergraduate degree for quantum.
Yeah, okay, got it. I must say, anyone listening to this wanting to pursue a career in QIC must listen to this advice very seriously. Thank you, Dr. Sandeep. We appreciate having you here and you taking out your time from busy schedule. Thank you once again.
Thank you, Adrika, and thank you the whole team. I really enjoyed this podcast and this recording. I was a little skeptical in the beginning that you are all high school students. So I was thinking like what kind of discussions we can have. But then after talking to you over emails, over messages, and today, I realized like you people are really enthusiastic and really want to take things forward. And it's good to see such initiatives from India. So I'm really looking forward to your success.
Thank you.